specify the effective radius of that galaxy. And here they found there are at least like two distinct groups of type 1 supernovae in terms of their ejecta velocity, measured from this silicon-2 feature. So you can see, for example, for these red ones, they are defined as a higher silicon velocity type 1 supernovae. So here they use 12,000 kilometers per second as a criteria to separate these two groups. And these blue ones, they're lower velocity, lower silicon velocity type 1 supernovae. So they found a tendency that this higher velocity type 1 supernovae, they tend to be found in an inner part of their galaxies. While these blue ones, these lower velocity type 1 supernovae, they can be found in both like inner part and outer part of their galaxies. So this is like very statistically significant result. And so of course, the interpretation of this is because the radial distance of to the center of the galaxy is not a very fundamental parameter, right? So they also think about what's the underlying source to drive this correlation. So naturally, again, it's metallicity. They think because there's metallicity gradient for galaxies, like for inner part of the galaxy, they tend to be more metal-rich than outer part of the galaxy. So they think it might be a metallicity which can to drive this relation, which one group of type 1 supernovae, in terms of its silicon velocity, they can they have preference on metal-rich environment, which is not the other group of type 1 supernovae. So this is further supported by another paper. So using a different parameter, use stellar mass. So if you it's sort of nearly the same figure, just I plot the radial distance instead of this stellar mass here. So again, I use the same criterion to separate this type 1 supernovae sample, and you can see for those high redshift silicon velocity sample, most of them have, most of their host galaxies have stellar mass of above 10 to 10 solar mass. But for this lower velocity supernovae, their host galaxies can be found in both low high mass galaxies. The ratio of the duration or the direction. It's like blue shift velocity.
Oh, okay. So you only know that it's
yes. Yes, we only measure absorptions. So these absorptions are caused by the blue shift.
Oh.
Yes. Okay. So this is, I think, it's another evidence that the metallicity might be a parameter we can use to separate, to differentiate between populations. Of course, there might be others, but it seems like the metallicity is very likely the underlying source. Okay, so yeah, almost finished. So one obvious question to ask is, why is metallicity, why is this metal-rich environment important to produce, for example, this high velocity type 1 supernovae? So I don't know the answer, but based on the current theoretical picture, so they think these high velocity type 1 supernovae, they are produced by sub-Chandra second mass explosions. So they think they are mostly produced by with a weight of mass way below 1.4 solar mass. So for example, so this assuming this is your primary weight of the binary system, and you give this weight of a layer of helium, right? If this helium has enough mass, it can probably trigger a helium detonation on the surface of the white dwarf. And this will drive a shock wave towards the center of this white dwarf. And again, trigger another detonation a carbon core detonation, and then produce this type 1 supernova. Yeah, the same thing. I hope this is pretty useful. Okay, so they think, based on this theoretical picture, they think most of the high velocity type 1 supernovae, they originate from this soft change of mass explosions. I think via this double detonation, there are two detonations required to produce this supernovae, because they think this kind of scenario can produce high velocity silicon velocity, because you have lower mass white dwarfs, and it's partly related to the binding energy, or ignite things on the surface white dwarf produce some high velocity elements. So it's very possible to for this kind of double detonation to produce this high velocity type 1 supernovae. But how does this metal-rich environments connect to this kind of scenario? Right, that's the question. To be honest, I don't know the answer, and most of these double detonation models, I don't think they consider this metallicity. They did not include this metallicity into their analysis.
So in this model, do you also expect to see helium atoms?
No. So that's only a small amount of helium. In their model, it's probably about 0.01, something below 0.01 solar mass of helium. So they think it's hard to detect if there's something that. Okay, so the question is how do we connect the metal-rich environment to this kind of scenario? So I don't know the answer, as I said, but naively I was think that if metal-rich stars, they tend to be tend to produce lower mass white dwarfs, right? Because they have more opaque, like stellar means, they have larger mass walls. So with such a low mass white dwarfs, it's probably difficult for them to be ignited near the Chandrasekhar mass limit. So it's far easier for them to explode as type 1 supernovae when they are still way below the 1.4 solar mass. And this is the one efficient way for them to do this. So, but that's just my guess, and I need theorists to do the hard work here. So there's other evidence. So if the populations of type 1 supernovae, they are sensitive to this metallicity, we should be able to see evolution with the redshift. So for example, this shows you a silicon velocity as a function of the redshift of our sample. You can see there's probably a decrease, like there's a change in the fraction of this high velocity type 1 supernovae towards higher redshift. So because at higher redshift, we expect them to be more metal poor. So it's hard for them, such environments, to produce maybe high velocity type 1 supernovae. But again, this sample might not be very complete at high redshift region, and I'm still working on the high redshift sample, try to see if this trend is real. If this is real, that's not evidence that metallicity must be just take effect on this, affecting the populations of the type 1 supernovae. And if there is a change, evolution of the redshift, then you have some trouble in cosmology, type 1 supernova cosmology. So again, so that's the end of my talk. Instead of a summary, I think I'll leave some unanswered questions here. So like, why the metal environment is necessary to produce type 1 superluminous supernova, and if there's really a metallicity threshold, like they claim there's a half-solar metallicity threshold for forming this kind of luminous events. And it's also not clear if the low redshift sample and high redshift sample, it applies to both sample, this metallicity effect. So, or it's, if there's an evolution due to the galaxy evolution or the evolution of the progenitors itself. Second, I think we have been talking a lot of the relationship between type 1 supernova, for example, their luminosity or ejecta velocity as a function of the host galaxy properties. But if the metallicity is really the underlying source to drive these relations. I don't know. There are also some people propose age might be also important, but this is still something still debated. And finally, I think, which is also the most important ones, so we try to figure out if the populations of type 1 supernova today evolve with redshift. So if they are sensitive to this metallicity, the metallicity of their host environment, we should be able to see this evolution. I think we need higher ratios of data. Okay, so that's the end of my talk.
Questions?
Can you explain more on the stretch? So, for example, how is the accreting mass related to the broadening of the light curve?
The critical mass.
Yeah, because I think, so if I understand it correctly, so the stretch the stretch implies how much mass is accreted to the white dwarf. Is that the case?
The width of the supernova lacquers is they're related to the peak velocity of the type 1 supernova. So therefore, it's their nickel 56 mass. It's related to the mass of nickel 56. But also the mass of nickel 56 also correlate with the total mass of the type 1A.
Thanks for the talk. So related to your second point. This page.
Second point. Okay.
Yes. So type 1A supernova tends to be found in more massive galaxies. So I wonder, how would you think, for example, for initial mass function, play any fundamental role here, or not necessary?
I don't know. I never think about this question. So you mean the initial mass of the stars?
Yes. In more massive and not so massive galaxies.
So I don't know what's I'm not an expert here, maybe. So what's is there a difference in initial mass function, like massive galaxies, low mass galaxies?
I don't think there are clear evidences.
Yeah.
Actually, I also wanted to ask a question.
Yeah, sorry, I'm not.
The same one?
Not exactly. It's a bit related to the question by Chen. So actually, because the metallicity measurements of the galaxies are reflecting the global properties of the galaxy, is it possible that it actually reflects some of the other properties like the density or the star formation activity or the overall activity of the galaxy, which might affect the supernova?
So if you plot like the supernova luminosity as a function of other parameters, you can still find correlation like star formation rate or something like that. But again, there's a degeneracy between these parameters, and it's really hard to really tell. But based on some evidence, for example, like the radial distance of the supernova, there's some trend between the radial distance and the ejecta velocity. You can use the radial distance of their location of these supernovae to separate populations. But I don't. So that's one I think. How does radial distance can correlate with star formation rate or age? I think metallicity is probably.
I wasn't going to ask this question because I still haven't quite worked it out in my mind. But when you talk about the radial distance, it's projecting. It's a projecting.
But for these galaxies, they deproject it using the excess ratio of the galaxy. But they didn't apply a correction on their distance ellipticals.
So on your velocity versus radius,
yes,
that's projecting.
Yes.
Radius. Do you have to worry about the velocity dispersion in that case? So if you're looking towards the core of a massive elliptical, the stars themselves might have 500 kilometers per second.
You mean the velocity dispersion of stars?
Well, yeah, the stellar mass in general.
Are you saying? I'm not sure I understand what your question. So do you mean
a velocity component to the supernova that comes from the projected velocity profile of the galaxy, which will be have a very kind of peak towards the center of the big elliptical.
So I don't think they consider this in their paper. Yeah, I'm not sure how that can affect. If it's a big effect.
If you have more scatter in the
Yes.
line velocity, and
So-
that seems almost comparable to
So I think they also separate simple into like spirals, these field triangles, and ellipticals are these open triangles. So if you only look into spirals, these triangles hold for.
with this, right?
Maybe I can make some comments.
Yes.
I think for one important question is it's still not very clear what are the progenitor system as well as supernova. So if there are maybe more population, then depending on the progenitor model, the delay time, which is the time between forming of the binary to supernovae, that could be also depending on progenitor system. And this delay time distribution is still, it actually should be sensitive with the initial mass function or the star formation history. But I mean, I think there's a study about this delay time distribution. But the next time that could be multiple populations. But still, at this moment, by just observing supernovae, it's probably still hard to say that how initial mass function change this evolution channels.
Thank you very much. So I have a very complex question. So you mentioned that the Hyper supernova can happen both in Quasar galaxy and Starling galaxy. Then the direction measurement for Starling galaxy is kind of straightforward. We can use emission, right? Then how do you do for Quasar galaxy? There must be difference.
Yeah. So for those like ellipticals, they measure the this absorption index.
Okay.
It's essentially the stellar metallicity, not the nebula lines. So you can fit continuum, with some stellar libraries.
What's the typical fraction of Quasar galaxy in your sample when you show the L-shaped distribution in mass metallicity? What was that?
Which one?
You mentioned the L-shaped data distribution in the parameter space. L-shaped.
L-shaped.
Could you
Yes. Okay. I mean,
before. This one.
okay.
What's the fraction of Quasar galaxy?
So I'm not sure. I didn't look into the morphology of these guys.
Okay.
Yes. So I don't major that one, but I think it's I don't think it's a minor population. It's probably substantial.
Then,
Maybe like 40% or yeah.
so just a moment. Yeah, I think we are comparing the two different methods here. So, yeah, maybe
So
it can be directed in this.
okay. So if you want, so for gas-phase metallicity, of course, it's kind of biased to star-forming galaxies. But these things will be more complete here. For stellar metallicity, which is on right here. Basically, I measure both star-forming and elliptical galaxies.
Okay, right around the stellar metallicity.
So we can still get stellar metallicity
Okay.
using star-forming galaxies. Yes.
Another question.
Sure.
So, the pipeline supernova is very important to constrain cosmological parameters.
Yes.
So, how much is this metallicity density affects on the metallic accuracy of cosmological parameters? Say, Hubble constant.
So on Hubble constant, that would be, I think it would be very minor, actually. I mean, compared to other uncertainties we are worried about at the moment, like trigonometric uncertainties, this kind of host dependence still just a very small fraction of your error budget.
But there must be systematic design.
So that's what we are worried. So if there is really evolution, which we don't know, then this might be important.
Oh, okay.
Yes. But I don't think there are not studies trying to give a quantitative, give numbers of how this metallicity evolution will cause uncertainties, the shift of your Hubble constant or something.
I was just expecting that this may be one solution to solve the application of Hubble consumption.
Probably not.
Probably not.
Probably not. I think it's not going to have huge contribution on your Hubble tension.
Thank you.
But to presume, trying to get a very high precision type 1 cosmology, that's still something. It's kind of maybe the second order effect. But after we take out all the major uncertainties, that become the major part of our uncertainties and host dependence. Yes.
Earlier on, you had a plot of just the galaxy metallicity versus galaxy mass with the supernova, the superluminous supernova plotted on it. Just the mass metallicity relation.
Mass of
So the galaxy mass metallicity relation, and then you put on there the host of the superluminous supernova.
You mean
Great point. Earlier,
for superluminous?
Yeah.
Okay. I thought that's
That one.
yes.
So how do ordinary core collapse supernova look visibly on this plot?
I think I don't remember about core collapse, but
Or whatever we should be comparing to the superluminous?
it depends on what types of core collapse so for example, I think for like type 1b or type 1c, they tend to be higher metallicity, for example. So it really depends on the subtypes.
So the ordinary types go away with the lower metallicity and lower mass end. The superluminous types appear there. So it's not like there's a
I'm not sure if there's studies trying to compare. Metallicity. It's a plot. I didn't show this. So there's no supernovae, but it's the oxygen abundance, like gaseous metallicity for different types of cold type supernovae. Yeah. So for superluminous supernovae, most of them are below 8.4. Yeah, I think 8.4. So it's kind of here. It's like a very different.
There are a few regular normal looking.
Yeah, sure. Yeah.
So back to your previous plot, the velocity versus
The previous plot.
The one before that Andrew was asking.
Okay.
Yeah. I vaguely remember this similar behavior for the GRB hosts. Have you
Yes.
compared the
Sure.
distribution and how can you learn something from that
So
comparison?
for example, like long GRBs, there's a preference on low metallicity there, but I don't think they're that extreme.
Oh,
Maybe.
okay.
So they're plot for that, but I remember it's not that extreme like superluminous supernova. So, no, of course, there are some studies suggest there might be some association between long GRBs and superluminous supernova, but I'm not sure what's the current progress on this. I'm not an expert.
I think they are different application. I think the supernova is more extreme case in terms of metallicity.
I see.
Okay. That's what I remember. Yeah.
So I have a question for this. You mentioned that high velocity
High silicon gas.
that can be explained by this substructure gap as model.
Yeah, the current. People think. It's like
But this population is kind of considered like a minor. What's the fraction?
the fraction of this high velocity, I would say, substantial. It's about, I think, it depends on maybe redshift. To burn this models again. So the fraction actually is, I think, there's some implications here. If simply based on high velocity type 1 supernovae, it's only like 20%. And remember, this high velocity type 1 supernovae, they are also normal, spectroscopically normal. So here, in this talk, I only focused on a normal type 1 supernovae because I would like to figure out what's the major scenario for type 1a. So this, even for this high velocity type 1 supernovae, they are also spectroscopically normal type 1 supernovae. But at low redshift, it's probably like 20%. But the thing is, for the double detonation model, a high velocity type 1 supernovae, they are just part of. For this double detonation model, they can also produce lower velocity supernovae. So there is some overlap here. There might be some double detonation model here. Some lower silicon velocity type 1 supernovae are responsible for this, from these scenarios. So in total, I think for the double detonation models, these subchanged cyclic channels would be something like 30 to 40%. My guess, yes.
And also in your early slide, you're saying like there's a debate between subchanged cyclic and subchanged.
Yes.
And also single digit and double digit. So how these host galaxies that you can train, how can give some hints on what projector model everywhere.
So I really think the theories should stand out and try to explain why this metallicity is important, if metallicity is the case. So for example, why these subchanged cyclic explosions, why metallicity is important. Maybe once we got some hints or clues, we can have better understanding. Because just based on the observations, that's the best we can do. But we need some theoretical explanations. Yes?
Just some comments. Type 1A supernova used to be can be understood. Actually, maybe we think already understand the mechanism of type 1 supernova. But now, due to this variety and reach of the observational data, then we found out we don't understand about type 1 supernova. Because there are at least 7 types of different kind of explosion channels. And we don't know which one actually work. Maybe all of them work, or maybe all of them don't work. So there's the current status of the theoretical side about this 1A development. So I don't know, just a complicated convolution. But for the metallicity part, I don't think I think it's nothing to do with the initial mass function at this moment, because this metallicity I think is probably still, so Peter like I probably will work. For the most of the galaxies being observed in this case. But maybe some extreme case is in a very high redshift universe. However, the more important part is in the stellar evolution part, how the metallicity kick in the stellar evolution affect not only single star but also binary. Eventually, how they evolve into become the progenitor for 1A explosion. That's a big issue, and people are trying to do this. So we will see.
But then how can we use this as a standard cannon?
Yeah, that's a good point. That's a very good question. So actually, the thing is we don't understand the physics of the explosion that really well. However, observation of a type 1A actually show a very nice kind of regulation. I think the physics relation tell you about this, what's the relation between if you draw many supernova 1A lighter, and you will find the width and the brightness, the height of the lighter have a certain relation. And after you scale all of the different 1A lighter, and they all match up.
Physics relations are only valid for normal type 1A supernovae, but there are actually lots of curious supernovae which don't follow Phillips relationship. Yeah. But we can exclude that and then use only normal type 1A supernovae. And in that sense, the only question is how much nickel can produce, no matter how they produce. But if they are produced, then we can find this Phillips relationship and then to measure distance.
So actually, there are also two populations of people in this field, type 1. So for those working on cosmology, they don't really care what we are. They don't care if it's going to cost them any. So yeah, they think it's the current it's good enough by using simple standardization techniques. They can already do a good job in at least the stellar rate expansion of the universe is it's probably not going to be changed. This if there's even evolution of the type 1 supernovae, it's probably not going to change, make it opposite or something.
Yeah, I think the type 1A used as a standard handle for to decay until redshift 1 probably is good enough. And then beyond you want to see something earlier, probably you need a superluminous supernova. But that's still uncertain.
For superluminous supernovae, there are some studies suggest that they can also be used in. There are some people trying to use superluminous supernovae as standard candles, like type 1A.
Yeah.
But still, I think it's still a very long way to go.
Yeah.
If it's if it works, I think we can probe the expansion of the universe up to redshift 2 or even 3. So that's pretty promising.
That's maybe another Nobel Prize.
The theoretical candidates for the type 1A supernova, except for the binary arrival binary.
I think all the scenarios all include a white dwarf.
At least one.
At least 1 or 2 white dwarf.
Because
And the other competing star, whether they accrete, and certain different kind of nuclear burning made on the surface. For example, either will accumulate a lot of energy, a lot of mass on another white dwarf, and that's exceeding Chen mass and collapse and explode. That's one type. The other type is you accrete, but just like this model, they have a detonation occurs, and detonation will surround this white dwarf, and will compress and central ignite the carbon upstream detonation bomb. In the time, or 2 of the white dwarf, they merge and receiving the second bomb.
So the uncertainty is between these two models.
Actually, there are some fine detail about the individual models.
So yeah, it's pretty sure. We're pretty sure it must be exploded as white based on, for example, there is some evidence from very nearby type 1 supernova, like 11FE, 2011 FE. We got this supernova very early, and based on its very early timeline curves photometry, we constrain the size of the progenitor to be a compact object. So it must be white dwarf explosion. But the problem is how to trigger this white dwarf.
Maybe a stupid question, but why not neutron star?
Actually, I was working with a student at Tokyo University, and then I tried to explore the merging between the neutron star and the white dwarf, whether the neutron star, when they merge with the white dwarf, whether it can trigger another sort of explosion on the ignited explosion for the white dwarf, produce something like type 1A. That's possible. That's possible.
So for neutron star merger, we know its differences from this gravitational events, GW, exactly, holes, and similar. So we know neutron star merger actually is a different event.
So I think in the future, once some gravitational wave detector, like space-based telescope, gravitational wave detectors, coming online, maybe that's our opportunity to really know if it's double white dwarfs or. But still, before that.
So for the superluminous supernova, that one, because if the progenitor is 35 solar mass or higher, massive stars, then it must be very sensitive to the IMF. Very sensitive to the IMF. And from the imaging of the host galaxy, can you estimate the IMF and whether statistically that kind of thing can occur or not? Can you discuss about it?
I don't know if we can, based on like just host photometry or something to determine IMF. Usually we assume an IMF and then we determine host properties. But if it's going to be
well, that is probably stellar synthesis method or something. If you have several
so I'm not sure.
Filter image.
For superluminous supernovae, is it the current model? Is it like a very massive star? Because it's hydrogen free. Because you need some mechanism to get this envelope straight.
Well,
anyway,
can talk 35 solar mass
Yes.
higher.
Yes, actually, I mean, when you discard the mass, please you sort of pay attention to the mass here, because whether you point out this initial mass of the star, or at the final time, at the final moment when the star dies, those two mass can be very different.
Oh, yeah.
Yeah.
But
So
it was originally
it originally like a 35 each solar mass. And during this all the main sequence, post-main sequence, all the evolution, probably shutting the mass probably down to about 10.
Yeah,
Also,
but still, IMF up to 35 is really extreme.
Yeah, but that's why the supernovae and supernova also very rare.
we know that we have some galaxies where you have formed whatever solar mass.
Yes, like just solar mass. Yeah.
So if that really is working like a sort of continuous IMF, then all of the slightly less massive stars might still be there. So
Yes.
you might expect to see a lot of supernovas.
Yes. But another thing is when you observe, it's probably sometimes can be difficult because for this supernova usually observed in the dwarf galaxies. So usually not obscure region. So you see this supernova. However, if you have massive star formation on the very center of the galaxy, then that will be a problem to be observed.
But then, assume our galaxy's magnetar is progenitor of this kind of thing. Then, from that observation, that it's more local, close, then you can probably estimate the IMF around the magnetar. And very localized IMF, and whether that kind of statistically possible or not can be discussed. But I don't know who would do this. Is there any such kind of discussion?
Yeah, I don't think they're like studies papers trying to figure out like IMF, from this direction to try to interpret progenitors. Might be a good way to try, but I don't know.
What are the distances? What are the distances to the superluminous supernova dwarf host?
So for the one I showed you in this talk, it's redshift about below 0.1.
That's a good start.
I mean, they're the most nearby superluminous supernova now is like 0.03 or something like that. Mostly, probably only one or two of them.
Okay. That's
Still too
far.
Yeah, there's no extremely nearby one. Or we can do something like pre-exploding imaging analysis.
You might be able to tell very, very good colors and all that.
So yeah, again, it's very rare. I mean, for this kind of supernova, at least for the local universe, it's rare. And remember, there's an increase in the rate of the supernovas until, I think it's peaked at around redshift 2, which is something expected, the peak of the star formation.
Just advertisement to our NCTS activities. Since Ken mentioned about the Nobel Prize, Adam Rees, John Hopkins, he will give us a talk, a remote talk, this December in our NCTS annual field meeting. If you're interested, just visit the website.
Any other questions? questions? We have 7 minutes.
I guess. Some crazy ideas. Has lensing been completely ruled out? Lensing, gravitational lensing, been completely ruled out as a cause of supernova and supernova?
It should be obvious. I mean,
the thing is those are for the lensing. People have been trying to start. This is one example by Kelly. There's one example for detection of the gravitational lensing image for complex supernova. That's one, at least I don't like one. And the supernovae and supernova, in most of cases, at least from the image or from the spectroscopy analysis, they didn't show like a sign of the being lensed by the halos. So
micro lensing is too crazy.
Yeah. So lensing is not the reason to magnify the luminosity.
I don't think there's any detecting caused by lensing.
Superluminous.
Yeah, first luminous.
Yeah, I think the fact is no further question. We can maybe have a break, and then at 3 o'clock we will take group photo. I think because the weather is nice, maybe we can meet probably downstairs. I will check with our secretary. But yeah, so just take a break here and then wait here. I will announce when exactly we will meet for group photo. Okay, thank you. So let's thank the speaker again.
各位还需要些时间了解，感觉最近这几个礼拜已经比较忙一点，应该也蛮忙的。所以你要到哪去？他现在昨天有去。OK， 对，1楼。
So 现在买市场。